Okay, hello everybody. My name is Jordi Bieger. I'm a PhD student at the Center for Analysis and Design of Intelligent Agents at the Garrett University. And I'm going to talk about raising AI and tutoring. The paper I wrote together with my PhD advisor, Thórisson, and Deon Garrett from the Icelandic Institute for Intelligent Machines. I think the goal that we all probably want to realize is to have an AGI system that is in some way useful to us and can realize our goals, can be sort of a productive member of society, and I will be referring to that as sort of an adult level AI. We often talk about human level, but I think that the end goal is for the system to be able to do something useful for us. And in order to get there, we have two main phases, I think. The first, of course, design and implementation of a cognitive architecture that I think most people here are focused on. But once we have that realized, the system, at least in most people's views, I think, still doesn't have a whole lot of knowledge, cannot really do much yet. And we can sort of view it as an artificial baby. And then there is a phase where it has to learn, has to grow up, has to develop into sort of that productive adult. And I'm going to talk a little bit about this learning phase, which I think is also important, and I hope to convince you of that. So, in a typical AI project, not every AI project, of course, machine learning project, it seems that we are making the assumption that the system only learns on the final task. So, if you think of a task like doing object recognition in video, then we just show it a whole bunch of videos with annotations, and we expect the system to learn in the full complexity of the environment that it has to perform in when it's an adult. Furthermore, very often the system is assumed to be alone. It's the only AI, and it learns from a data set, and it goes over that again and again and again. And again, there are of course exceptions, but this is a very common scenario that we see in machine learning and artificial intelligence. And I would like to challenge that a little bit and talk more about how we can help the system go from the baby stage to the adult stage and help it realize its potential intelligence. So why do we have to raise AI system? And when I say raise, I mean like raise like a child or like a baby, or and of course we will have to find some kind of artificial analogy to how we do it for humans and other animals. So the first is that I think that if we want our systems to be complex and to work in complex environments, then guidance is almost necessary to be able to deal with that. If you imagine having a wide range of options and sequences of actions that you can perform in a very complex environment where only a few of those sequences are ever going to result in a kind of feedback that you can use to learn from, then starting out with no knowledge and basically the only option is to move about randomly until you stumble upon something that you can learn from, then that's going to be intractable, and you really use some guidance. I think probably most of you are familiar with the DeepMind paper on learning Atari video games, and they did really, really well. But the one type of task, the one type of game that they couldn't really learn was where the system took a really long time from the first initial stage, where it doesn't know anything yet, to stumble upon good action that it can then learn from and backtrack to understand what actions are good. And I think that a tutor or a parent or somebody to guide the system there could really help. And this leads me to the next point, which is that if you want your system to work completely from scratch, I just think you're going to need a vastly more sophisticated system to deal with this issue that I just related. And although we have to design the system in order to be able to take advantage of the tutoring, of the raising, I think that it would be a much more practical problem to develop a cognitive architecture that we can then raise, rather than develop a cognitive architecture that can then learn completely on its own. And finally, it's just biologically plausible. Dr. Granger talked about existence proof of human intelligence, or of general intelligence, and really the only existence proof that we have are humans and maybe some animals, and all of those raise their children. We grow up in an environment with parents, teachers, other children that we can look at and learn from. So that's another reason why you might want to do this. The goals for the paper were to argue for the importance of research into raising AI. I've already talked about that a little bit, to discuss some issues that are related to raising and tutoring, to unite some research from different fields and a perspective of raising AI, because although I have said that the typical AI or ML project doesn't really do this, there are of course many efforts underway that have incorporated ways of helping a system learn during its lifetime. And Dr. Benchio has been working on curriculum learning. I cannot really go into that now, but Ben Gertzel has talked about AGI preschool, and there are, we try to teach robots by demonstration sometimes, and there is of course a lot of effort on teaching and tutoring and raising in areas like developmental psychology as well, and I try to bring it all together under this perspective, and we want to provide a starting point for various techniques that could be adapted to work in an artificial domain. So why do I talk about tutoring rather than raising? The reason is basically because I think when you really talk about raising, you want to be able to guide your system through what Dr. Granger thought was the development stage rather than the learning stage of the system's life. And I think that's probably much more interesting, but I'm only at the start of my PhD and I haven't gotten there yet. So I will be focusing now on learning tasks. One reason I think it's important to consider how to raise or tutor AI systems is that as humans we are only capable of teaching, of tutoring in certain ways. And we have to keep that in mind while we are building our cognitive architectures. You might think that you can just build a cognitive architecture and then later worry about how you're going to go about teaching it and giving it knowledge. But I think it's much more efficient if you think about that beforehand and then you develop your teaching curriculum, tutoring curriculum, more or less at the same time that you are developing the cognitive architecture so that they are fully adjusted to each other. Another reason I think research into this field needs to happen is that although it may seem obvious that of course if you help the system it's going to do better, that isn't really the case. It doesn't always work. There are many situations in which you can actually harm the system because in the end of course you want it to be autonomous and to be able to work without a tutor. And sometimes tutoring in the wrong way can make it not learn how to do it something on its own. So you have to really think about how to do it, and it can be very difficult. And finally, we have to consider whether it's worth it and in what cases it is worth it. Because if you require a human tutor to be there all the time for your artificial system, that may be very expensive. And furthermore, humans are pretty slow. If you have a virtual agent in a virtual environment, it may be able to do many steps of learning, many thousands maybe, in the time that it would take a human to give advice on one single step. And then it may be the case that the system learns in less steps, but may not offset the actual time that is needed. So this is why I think we can definitely get benefits out of tutoring and raising our AI systems, but it's not obvious, and we really need to think about how to do that. And I hope to do that and then next year report back to you. In the paper we have listed 9 different kinds of tutoring technique that come from various fields of research, and we've connected that to existing research so that you can read about that, but I don't really have the time to go over all of them. So I'm just going to pick one, which is tutoring by demonstration, which is basically you show the learner what it has to do by performing the task yourself. This is a fairly well-known way of teaching, of course. It ties into fields like imitation learning that are often used in robotics. And we did this for most of the tutoring techniques that I briefly listed on that other slide. So we tried to illustrate how you could go from this sort of abstract idea of tutoring by demonstration and learning by imitation to how you could do it in an artificial system. And to illustrate that, we have a very simple grid navigation task. You can see the robot baby avatar, and its only goal is to move towards the center of the grid. And it has to learn to do that from every single cell, and there's no noise, there are no obstacles. It's really very simple. It's not meant to be AGI, it's just for illustration purposes. The agent itself is just tabular learning agent. If you know anything about reinforcement learning, this is probably the algorithm that you learn. For those who don't know, the system gets a reward when it comes to treasure, and it tries to find a policy that will allow it to get there. And the tabular Q learning agent is going to have a lookup table for state action pairs that has a Q value, which basically estimates the value that it expects to get if it takes that action in that state. So in the normal task, it's just two-dimensional state, x and y coordinates of the agent, and it can take 4 actions up, down, left, right. And we want to help it learn this very simple task, and to do it by demonstration, we added 2 more dimensions to the system that basically tell it where the tutor has moved just before it has to move itself. So you might be able to see how that is teaching by demonstration, but you might also be able to recognize some issues with that, because first of all, we went from a 2-dimensional state space to a 4-dimensional state space, which greatly increases the size and might actually take it to way longer to learn. But furthermore, the tabular learning agent cannot generalize at all. So if we're going to take the tutoring signal away at the end, which we are going to do because we want it to be able to do things on its own, then it will look like it is a completely different state, and it won't remember anything it learned, basically. So that is a problem. And I'm telling you this to illustrate that even something that might seem like a good idea, like tutoring by demonstration, isn't that straightforward, and you really need to design your agent in a way that it can deal with that. So what we did was to basically say, well, okay, it knows that its own location is different from the signal gets from the tutor, so we implemented 2 different Q tables and then had them sort of vote on which one was more confident, and then it works pretty well. And there are other things that you can do there. Ideally, you want it to have sort of a desire to imitate, which we can, I think, sort of observe in human babies. They imitate their parents, for instance, and then they also have to solve a very difficult vision problem of post-estimation, where they have to detect what's the other person's arm, how does that map onto my own body and how I move, and things like that. So we have some results for how this actually helped if you implement it that way, and it does. So I think there can be a great benefit in tutoring your AI system, in eventually raising the system with much more sophisticated methods. But there is definitely future research to be done to investigate how to best adjust the tutoring method to the learner and vice versa. That's it. I thought that you could ask questions, but I guess you have to do it in the panel discussion.